The purpose of this periodic table is to provide a visualization of the atomic orbitals and orbital hybridization that occurs in atoms. It's based on the nature of what the electron actually is as a self-confined photonic wave structure. So before we start with the periodic table, I'd like to just take a moment to visit this link right here, Understanding Electrons. And here we will see a brief description of the electron according to the Williamson-van der Mark electron model. It was developed by John Williamson and Martin van der Mark, published in a 1997 paper, which you can find here on the website. Essentially, it describes how an electron is a confined photon topology. This structure here shows the interchangeability between energy, E, and matter, the electron, M, mass. This kind of gives a nice visual of E is equal to mc squared, showing the interchangeability between energy and matter particles, in this case, the electron. I'd also like to point out some details about this diagram because it can be misleading. If you imagine a photon, a circularly polarized photon traveling straight, now if you imagine that it became self-confined into a double loop rotation, after 2 rotations, the electric and magnetic fields align perfectly with themselves, which allows the photon to phase lock with itself into a stationary wave structure, a spherically harmonic, spherically symmetrical stationary wave structure. Now this looks like a toroidal structure, which is not spherically symmetrical, so I just want to take a moment to explain what you're looking at here. This diagram is a composite image of 2 different images. The toroidal shape, it's describing the momentum configuration in a momentum space, which is not the same as 3-dimensional space. It's a space in which we're visualizing a mathematical transformation, which is a cross product between 2 other vectors, creating a bivector space. So without getting into the technical details, if we were to reflect this into regular 3-dimensional space, it will transform as a spherical and a spherically symmetrical electron wave structure, and that is why it manifests as a spherically symmetrical charge, even though its momentum on the inside is not spherical, it's toroidal. I don't want to go into too much detail about the electron, even though it's fascinating and an important topic in its own right. Feel free to browse this page on our website to the depth of your interest. I would like to point out, though, that when electrons combine into an atom, they form a single new quantum wave state. It is no longer made up of separate entities, but they merge into a single entity which cannot be subdivided. If you were to remove any element, it would disrupt the system and it would have to find a new equilibrium system. So this image at the top here is really a spinning string, which is designed to evoke the idea of a linear wave. And what you see here is a wave that's a standing wave structure where it has 2 lobe structures. Now, if you could imagine transferring that into 3-dimensional space, into a spherical situation, this would be an example of a 4-directional wave in a spherical arrangement. Those of you that know chemistry will recognize this is the sp3 orbitals that you can find in the second shell of the carbon atom. Now, these 4 directions are going to be as far away from each other as possible because electrons repel. The traditional view of their structure looks like this, where you have 4 lobe shapes. However, we believe that these images on the right reflect a more realistic view of what that electron wave structure will actually do. This one shows the shell divided into 4 equal segments, 4 equal tetrahedral segments, and this represents the same thing except showing it more as a wave structure with nodes and internodes more clearly defined. Do notice, though, that nowhere on the surface is there 0 electron density. The electron density has to be spherically symmetrical around the nuclear core in order to cancel the positive charge in all directions. On this page is a little bit more information about electrons, how they arrange themselves initially around atoms, but we're about to get into that right now. And if you scroll down further, you can see a diagrammatic representation of the concept of how electrons of opposite spin will superimpose to form a dielectron or a covalent bond. and this is what it would look like in helium. That's what it would look like in the hydrogen molecule. There's more information here, but I will leave you to investigate that at your interest. But for now, let's return to the periodic table and look at the first 10 elements of the periodic table. So if you scroll down below the periodic table, there's a key to clarify what we are going to be looking at and what these shapes are actually meant to depict. If you have a very light colored wireframe orbital, that's meant to show that it only contains a single electron. If it's a brightly colored orbital, it's meant to show that it contains two electrons, a pair, a dielectron, or a Cooper pair, if you will. Now, when we go on to the more complicated atomic structures, this would be the carbon atom. You'll notice its first shell has 2 electrons, but I want to clarify that these 4 electrons are not meant to imply that the lobe shapes are circles or spherical little spheres. They are not. These are just meant to show the directions around the central core, the directions of maximum electron density. So this is really just designed to show geometry, not the details of exactly where the electron density resides. Further down, there's some links to some molecules, some periodic trends about how various properties change predictably across the periodic table, and down some more information about some geometry and some related concepts that we delve into about magnetism, etc. So you can look at those things at your leisure. For now, let's jump into the first element, hydrogen. So hydrogen is the first element because it contains only one proton. That's called the atomic number, and it determines the character of the element. Hydrogen will have one electron because electrons are negative and protons are positive. So the presence of a proton will attract an electron to itself, and then they will wrap themselves in one another and form an atom which will be neutral overall because it will allow the positive and the negative charges to cancel each other out. Hydrogen has a mass of 1. Now the mass of 1 refers to the proton, because protons are 2,000 times heavier than electrons. So we don't count the electrons in the atomic mass, we only count the protons and the neutrons. And since the vast majority of hydrogen atoms do not have a neutron, the atomic mass will be 1. If we scroll down, there's going to be some more information about the hydrogen atom. The first thing I'd like to focus on is its electron structure. The hydrogen atom has only one electron, so it will form a single shell. So we represent that by the term 1s1. 1 refers to the first shell. Hydrogen only has one. S refers to this type of orbital, which is a spherical shell. And the number 1 represents the number of electrons that are in that spherical orbital, which in this case is 1. If we scroll down further, you will see that there's another representation here, just trying to evoke that idea of electron density around the nucleus. I must also point out that the nucleus is highly exaggerated in size. If the atom were the size of a football stadium, the nucleus would be the size of a penny placed at the center of the field, which means it would pretty much be invisible from the stands. This relative size block indicates how big the hydrogen atom is compared to the largest atom on the periodic table, which would fill this square. Also, this color-coded bar along the bottom is meant to indicate the electronegativity of the hydrogen atom. That is a measure of how strongly it holds onto its electrons. Those atoms that would be purple would hold their electrons very strongly and not want to let any of them go. Those on the red side would hold their electrons rather weakly, and some of them would be able to be taken by another atom who wants electrons much more strongly. Atoms can form ions, which means that the balance between the protons and the electrons is no longer 1-to-1. There's either more electrons than protons, in which case the atom will have a negative charge, or there's more protons than electrons, in which case the atom will have a positive charge, and that is called an ion. When hydrogen loses its electron, it's called the positive hydrogen ion, and that is actually simply a proton because it has no electrons around it, which makes it a highly reactive state, and that is actually what defines, that's one of the definitions of an acid, is a substance that has these exposed protons, because that will forcibly pull electrons from other atoms. the opposite of that would be a base, which would be, in this case, an atom that has excess negative charges. In that case, it will be able to attract and neutralize something that's acidic. Now, that's a simplification. There's more to the acid and base conversation than that, but I did want to simply draw that connection between the concept of the positive and negative ion and the concept of acid and base, which is related. Now, if we scroll down further, you'll notice that if we have two hydrogen atoms, they will very happily combine because their electrons then get to form a dielectron state, which is highly stable. So this is a picture of what the hydrogen molecule might look like, with two nuclei suspended within the dielectron's negative charge field. The two protons of the hydrogen nuclei are kept apart by their mutual repulsion because they're both positive, and they are attracted and held in place by the negative charges around them that are attracting them. At the bottom of this page, there's some detail about the importance of the hydrogen atom, its role in cosmology, its role in space travel, and even its role in electricity and batteries, which is fascinating. The second last thing on the page deals with hydrogen isotopes. An isotope is an atom that has a different number of neutrons than usual. Now, ordinarily, most hydrogen in the universe, 99.98% of it, only has a proton and no neutrons, and that's called protium, although we just call it hydrogen. If it has one neutron, it has a mass of 2. That's called deuterium. If it has 2 neutrons, it'll have a mass of 3, and that's called tritium. Finally, at the bottom of the page here, those that are interested in delving into the hydrogen atom from more of a quantum mechanical point of view, it's interesting to note that a very small proton and an electron in free space that is 1,000 times larger combine to form a nucleus that is again 100 times larger than that. What's interesting to note is that in terms of the electric field, the proton fills the entire sphere of the atom and the electron fills the entire sphere of the atom. They are two superimposed wave states that completely fill the space of the hydrogen with their charge. Now, obviously, the further we get from the center, the more of the positive charge has been cancelled. The more we get towards the center, the more of the negative charge has been cancelled. So it's not necessarily that they are equal in their distribution, but they do both, in a very real sense, they are both wave structures that fill the entire volume. So I will leave you to look at all the details if you are interested. Let's now move on to the helium atom. Helium has 2 protons because it's element number 2. Actually, it's element number 2 because it has 2 protons. It also has 2 neutrons, giving it a mass of 4. And its 2 protons will attract 2 electrons in order to make a neutral atom. So this would be the structure of the helium's shell. It also only has a single shell, an s orbital. S orbitals can accommodate 2 electrons, forming a dielectron similar to the hydrogen molecule. Here is the glossy view. We'll also notice that helium is actually the smallest element on the periodic table. This diagram represents the nucleus of the helium atom according to the Robinson model of nuclear binding, which I highly recommend that you look at. It is the most intuitive and clear explanation I've ever come across for how it is that protons and neutrons can bond to make a nucleus, given that protons are positive and neutrons are neutral. They shouldn't be able to bind, but yet they do, and the Robinson model explains it in a beautiful way. So this would be the nucleus of the helium atom. It is also known as an alpha particle when you strip away its electrons, the helium 2+ ion, called an alpha particle, and it is one of the forms of nuclear radiation that large atoms can emit when they decay. Let's move on to lithium. Lithium is the 3rd element on the periodic table. It has 3 protons, 3 electrons to balance the charge, but it actually has 4 neutrons, giving it a mass of about 7. The fact that it's a 6.9 is an average. If you factor in all the isotopes of lithium, including those that have 3 neutrons, it lowers the average slightly below 7. Now, lithium's 3rd electron fills a 2nd shell. You will also notice lithium is the first element on the second row of the periodic table. That is not a coincidence. It is the first element with an electron in the second shell. And that is how the periodic table is designed. So now the first shell can only accommodate 2 electrons. That is because it's very small. And therefore, once you have a dielectron that is formed, no other electron can enter that first shell, which means in order to approach the nucleus, since it's attracted to the nucleus's third proton, it has no choice but to wrap itself around the inner shell to try to get as close as it can. So it's the electron configuration of lithium would be 1s2, 2s1. The 1s orbital has 2 electrons in the middle, and the second shell has an s orbital now with a single electron in it. If we look at lithium's size, you'll notice it's significantly larger than hydrogen. Also, lithium has a single electron in its outer shell. Now that is neutral. The atom is neutral overall, which is stable from a charge point of view. But from an electron interaction point of view, that's not stable. Electrons do not like to be by themselves because they're asymmetrical. They're spinning in one direction, and therefore they're not balanced. So this atom would either like to gain an electron or it would like to lose an electron. Now, for reasons that we'll get into later, it will choose to lose an electron. If it does so, it now becomes a dielectron state, which from an electron point of view is very stable. However, because it lost an electron, it now has one more proton than it does electrons, which means the atom is now overall has a positive charge. This also shows us something very interesting. It's more important to an atom that its electron situation is well balanced than that the charges are well balanced. Atoms would rather be an ion than be neutral if it means that their electron configuration is highly stable. Let's move on to the next element, which is beryllium. Beryllium is element number 4 because it has 4 protons, it has 4 electrons to balance that charge, and it has 5 neutrons, which gives it a mass of 9. Its electron configuration, you could probably predict, is going to be 1s2, 2s2. It has 2 electrons in the first shell, and then it has 2 electrons forming a dielectron in the second shell, which gives beryllium a very interesting structure in its neutral atom form of a dielectron within a dielectron. Now, beryllium is slightly smaller than lithium, and that is because it has more protons in the center, and those more protons are therefore pulling more strongly on the electrons around it, and that has the effect of shrinking the atom down, and that is called effective nuclear charge. You can look at it following this link. Also notice that the electronegativity of beryllium is very low. It's on this end, which means it is willing to lose electrons rather than gain them. As such, beryllium can lose its 2 outer electrons and form a 2+ charge in its stable dielectron state. There's more information here for those interested, so moving on to boron. Boron is element number 5 with 5 electrons and 5 protons and 6 neutrons on average, giving it an atomic mass in the vicinity of 11. Now, boron is very interesting because we are now adding a 3rd electron in the second shell. Now, the second shell has already a dielectron. It has 2 electrons in a very stable configuration together with one another, and now we're throwing a 3rd electron into that mix. Now, this shows what will not happen. You cannot have this single 5th electron just throwing itself into the second shell because it creates an asymmetry. And electron wave structures require symmetry in order to be stable. Now, those of you that have learned a bit of chemistry will recognize this. This gives you the shape of the next kind of orbital after the spherical s orbital. And it's called a p orbital, and it has 3 directions, x, y, and z. And each direction has 2 lobes, which can contain 1 electron's worth of electron density on average. That means if we had 6 electrons, according to the basic theory, they will form this structure. But as we will see, that actually does not occur in reality. Now, what will actually happen when we plug this 5th electron into beryllium? An interesting thing called hybridization will occur. This is the electron configuration of an unhybridized boron atom. You have 2 electrons in the 1s, 2 electrons in the 2s like beryllium, and the 5th electron entering the new p orbital. Because this is asymmetrical, what will happen is these 2 electrons will raise their energy slightly, this one will lower its energy slightly, and they will arrange themselves in a symmetrical way where the energy of the 3 electrons is now equivalent, and therefore they will make a symmetrical 3-directional form called trigonal planar in molecular geometry. This is a more realistic view of what those orbital shapes may actually look like. As we said before, those 3rd shell electrons must fill the entire 3rd shell in order to cancel the electric field of the nucleus in all directions. What will happen though is the electron density will be strongest towards the center of these shells, and it will drop off and be minimized at the nodes where the orbitals meet. It will not be 0 though, because again the nucleus needs electron density in all directions around it. So this would kind of be like 3 slices of a watermelon, if you want to visualize those 3 orbitals. Here is the size of boron relative to the rest of the periodic table, and also notice its electronegativity is right in the middle. Moving on to element number 6, which is carbon. Carbon has 6 protons, it therefore attracts 6 electrons, and it also has 6 neutrons, giving it a mass of 12 on average. Once again, we have now 2 electrons in the p orbital, and this diagram shows how that would be asymmetrical if we simply tried to put them into normal p orbitals. So carbon will also hybridize. It will combine its 2p and 2s electrons into a single 4-directional configuration, allowing them to be equal energy and equal in their angles that are separating them. And this is called a tetrahedral arrangement, which means 4-directional. 4 single electrons around a dielectron in the middle. By the way, please note that this outer wireframe is simply to show the boundary of the shell. It's not meant to show that there is another electron there, because carbon only has 4 electrons in its 2nd shell. Here is again a more realistic view of what those orbital shapes might look like. This is the traditional chemistry view of the lobe shapes, and this is what we feel will be a more realistic view. Carbon is also a very small atom with a middling electronegativity, which gives it very powerful interactability with many different kinds of shapes and structures. It can make multiple different directionalities around its 4 directions, and therefore it can be found in many different types of molecules in nature, everything from coal to graphene to diamond to organic molecules like DNA and protein. This shows you how the natural gas, the methane molecule, forms. I do want to point out though that it doesn't form by 4 separate hydrogen atoms joining a separate carbon atom. It forms usually when you have hydrogen molecules that encounter carbon, and then when they interact they obviously separate and rearrange themselves in this way. But you can straight away see why this is such a stable molecule. All of the bonds between the hydrogens and the carbons form these dielectron interactions, where they are sharing an electron between the hydrogen and the carbon, which bonds them together very strongly. This picture does tend to make it look like these orbitals are separate from each other, but please note that they are not. This is just showing you the directionality, but those form a continuous wave structure. And at the bottom there's a little bit more interesting detail about carbon in nature. It's a fundamental building block in nature. It's part of photosynthesis, and it's part of the nutrient cycle for all living organisms on the planet. Moving on to nitrogen. Nitrogen, element number 7. 7 protons, 7 electrons, and 7 neutrons gives it a mass of 14. Nitrogen has 3 electrons in the p orbital, again highlighting its asymmetry, which will cause nitrogen also to hybridize. Now, it's interesting, nitrogen will hybridize into 4 directions like carbon did, even though it has 5 electrons. The most probable reason for that is that the 2nd shell has more volume than the first shell, so it can contain more than 2 electrons, but it can contain up to 8, which limits it to 4 directions, 4 dielectron directions. And that's probably the primary reason that this happens. In any case, because it has 4 directions, but 5 electrons in those hybrid orbitals, 2 of them will pair up as a dielectron, forming a lone pair, as it's called, and the other 3 will form individual electrons, which are each looking to find a partner, because electrons don't like to be by themselves. And this is going to cause nitrogen to want to gain 3 electrons, which causes it to form the nitrogen 3 ion when it gains those 3 electrons. Notice also that when it does so, it will not only gain 4 dielectrons in its outer shell, which is very stable, but you'll notice that the atom also became a lot bigger when it became the ion, and that is because it has 3 more electrons than it has protons in the nucleus, which means that those nuclear protons are not able to pull on all of those electrons as strongly, which allows the atom to actually expand in size. This shows one of the primary molecules in nature involving nitrogen, ammonia, which is when 3 hydrogen atoms link up to those 3 single electrons in nitrogen's outer shell, and that forms this molecule NH3. Once again, where the hydrogens bond to one of the electrons of the nitrogen, you find dielectrons, and this is the lone pair from the nitrogen on the opposite side. What is important to notice about this molecule is there's an asymmetry on a molecular scale. The one side, the nitrogen pulls electrons to itself very strongly because it has a high electronegativity. If we go back to this chart, nitrogen's electronegativity is up in the blue scale, whereas hydrogen is down here in the green, which means that nitrogen's atom is pulling the electrons from these hydrogens more strongly than the hydrogen can pull them itself, which means that overall, the electron density in this molecule will migrate towards the side of the nitrogen's lone pair and away from the hydrogen end, which means that the end where the hydrogens are bonded will tend to feel a little bit positive. This is not a full positive charge, it's only a partial positive charge, hence the Greek symbol delta, and the other end will feel partially negative, and that will cause this molecule to behave in nature as if it were slightly magnetic or dipolar. It will attract the negative end of this molecule, will attract the positive end of an adjacent molecule, and that has very important properties in nature because it affects how these particles interact with each other. Moving on to oxygen. Oxygen, element number 8, 8 protons, 8 electrons, 8 neutrons, giving it a mass of 16. Here we have 4 electrons in the p orbital, which once again forces oxygen to hybridize. It has 2, 4, 5, 6 electrons now in the second shell. Its electron configuration is 1s2, 2 electrons in the 1s orbital in the middle, 2s2. It has 2 electrons in the second shell s orbital and 4 electrons in the p, but as you can see from this image, those hybridize. We once again go to our 4-directional symmetry, which is stable in the second shell, which causes the 2 dielectrons to occupy 2 of those directions and the 2 unpaired electrons to occupy the other 2 directions. So we have once again a tetrahedral arrangement with 2 bonding sites. And that will cause oxygen to form the famous water molecule, where 2 hydrogen atoms link up to these 2 spots, forming the 2 hydrogen bonds connected to the rest of the oxygen molecule. Once again, we notice that because oxygen has a very high electronegativity, even higher than nitrogen, it's pulling the electron density from the hydrogens even more strongly, which gives it an even more powerful partial negative charge on the oxygen side and partial positive side on the hydrogen side. And that also has profoundly important implications throughout nature. The most important one being hydrogen bonding, which not only holds the DNA molecule together, but also defines all of water's interactions in nature. Here we have another representation of that, focusing on the electronegativity issue and showing you the relative polarity on the opposite sides of the molecule. Now, as we all know, oxygen is extremely important for combustion. It's what happens when something burns, is the process of that thing combining with oxygen in the air and converting into new chemical substances. And we know that when natural gas, methane, burns in oxygen, it forms water and carbon dioxide. This is fascinating as well. When oxygen forms a liquid and you pour it through very strong magnets, it doesn't fall through under the force of gravity, it sticks to the magnets, which shows you that the oxygen molecule is a very strongly magnetic molecule, which is a very interesting subject in its own right, and I encourage you to look into that. Ozone is also a fascinating molecule. It's made up of 3 oxygen atoms. They have an interesting interaction given the asymmetry of the molecule with their electrons, and they tend to form something called a resonance structure, where they create a symmetrical arrangement of electron density around that structure. Moving on to fluorine, which is a very interesting atom. Fluorine has 9 protons, 9 electrons, and 10 neutrons, giving it a mass of 19. Fluorine has 5 electrons in the p orbital, meaning it's 1 short of having a full p orbital. Just like nitrogen and oxygen, it will hybridize, and its tetrahedral 4 directions will have 3 pairs and 1 single, which means that fluorine is very eager to find 1 more electron to bond with its last unpaired electron. This makes fluorine extremely reactive. In fact, it is the most reactive and dangerous element on the periodic table. Its electronegativity is all the way pegged to the far side, to the max, which means that it will pretty much forcibly remove an electron from any other type of element that it comes into contact with. This is showing you the 1- ion when fluorine gains that negative ion, often in a violent reactive fashion. So fluorine has to always be dealt with great care. Moving on to the end of the second row of the periodic table, neon is the 10th element, 10 protons, 10 electrons, 10 neutrons, an average mass of 20. Now we get to an interesting conversation. Does neon form this structure because it has a full symmetrical arrangement in its p orbital? It is our contention that it does not. It is our contention that it'll form a tetrahedral arrangement of 4 dielectrons. And the reason is simply that dielectrons are far more stable than are individual electrons trying to avoid each other in the same shell. We believe they'll have no choice but to forcibly interact and form this highly stable and much lower energy structure. So, this is what our orbital diagram might look like of the outer shell of neon. This is just showing a difference between those approaches. This is the 6-directional approach, which we might visualize more accurately with the lobe shapes like this, but we believe it will look like this. Neon is also a rather small atom because it has a high effective nuclear charge with 10 protons in its nucleus that are all very close to that second shell, which makes neon rather small. Now, if we look at argon, which is just like neon, but it's 1 row below, which means it has 1 more full shell. So it's a full second shell and a full third shell around it, which we're showing with this gray shell. Now, we believe that argon will form its outermost shell in such a way that those electrons are arranged anti-parallel and anti-prismatic, meaning in between the dielectrons, the tetrahedral electron in the second shell. And the reason for that is in order that the electron density can avoid each other as much as possible. You'll notice in this diagram that the center of this shell holds the highest electron density in the third shell, and that is aligned directly over the point where the nodes meet in the second shell, which would be the point of lowest electron density in the second shell, and that minimizes electron repulsion between the shells. And we believe that argon will therefore hold itself in this electron topology. Now that's the end of the second shell. I would like to look at one more situation, and that is salt, sodium chloride. Sodium is the first element on the third shell, so it has 1 electron in a third shell over the inner configuration, which looks like neon. Now, sodium has a very low electronegativity, which means it's very keen to lose that outer electron because it gains the stability of having a full shell, just like neon, even though it'll have a positive charge. Now, before we look at salt, let's look at chlorine, which is the partner of sodium in this interaction. Chlorine is one electron away from filling up its tetrahedral arrangement. It's like fluorine, but one shell bigger, which means chlorine is desperate to find one more electron to fill that orbital. So what happens is chlorine will form its ion by gaining an electron. So if we now look at salt, we can now see what actually happens. A sodium atom loses its outer electron to form the sodium ion, which is positive and stable. The chlorine atom gains that electron to form a full outer shell, which now has a negative charge. So you now have two atoms that have electron configurations that are absolutely stable, and they will therefore no longer interact with an electron. But they do have opposite charges, and therefore they will attract each other like opposite charges do, and the sodium and chloride ions will therefore click into place when they are near each other, and they will build a crystal structure which has a cubic shape. If you've ever seen salt crystals on the beach, or if you've ever evaporated salt water to form crystals in the bottom of a cup, you will see that they form these beautiful cubic structures. This is a picture from an electronegativity point of view. We'll notice that the orange, the low electronegativity of sodium, the high electronegativity of chlorine allows chlorine to steal that electron, forming the ions that then form the crystal. Now, what happens when you dissolve this crystal in water? If I place this crystal surrounded by water molecules that are polar and have a distinct negative and positive side, the clustering of those water molecules will be tugging at the charges, trying to compete with the attraction within the crystal. And if they succeed in tugging one off, this negative ion will be pulled off. It will automatically become surrounded by the positive end of all of these water molecules that will cluster around it, forming a hydration shell. Similarly, if the negative end of the water molecules are able to pluck a positive sodium ion off the crystal, they will similarly surround it and form a sphere of hydration, where the negative end of the water molecules are right beside the sodium ion. If we then have this dissolved salt solution and we place it in the sun to allow the water to evaporate, as the water disappears, the exposed ions will click back onto the crystal, given that the water is starting to leave. And that's how crystallization of salt can form again. And again, you can try this at home by simply letting a cup of very concentrated salt solution evaporate. All right, returning to the periodic table, we have now taken a look at the electron configurations of hydrogen through neon, and we also looked at sodium and chlorine. Feel free to browse the rest of the periodic table. It is a work in progress, so you may not be able to see the detail on all of the atoms, but we hope to continue the work and finish the periodic table as soon as possible. Also, I encourage you to take a look at all of the other materials that can be found on our Quicycle website. Not only the interesting details about chemistry that can be found below the periodic table, but we also have an extensive library of video lectures on all manner of topics to do with physics and electrons, and some to do with cosmology, as well as having several articles in our journal, both published exclusively here as well as published elsewhere by some of our members, and several other interesting items, particularly a glossary full of many, many interesting terms, which I encourage you to look at. So I appreciate your time. Thank you for your consideration, and have a wonderful day.